All right, welcome back to the Math Professors. This is a YouTube channel that covers all sorts of subjects from algebra through calculus, differential equations, and so on. So please consider watching and subscribing and liking. So today I'm going to cover double and iterated integrals over rectangular regions. And I'm going to start out with the basic integral that we're taught in Calc 1, the integral from a to b of f of x dx, or a definite integral, which we know can represent an area underneath the curve. So the way this is done is through the Riemann sum, that we have a whole bunch of rectangles here where the height of the rectangle happens to be f of x, and then the width of this rectangle happens to be the change in x. And as you increase the amount of rectangles or decrease the change in x width, you're going to get an infinite amount of rectangles. So that change in x ends up becoming dx. So now you can see it's really the sum of all the heights times the widths. So that's why we get that area representation. Now, if we want to do this in 3 dimensions, like in a Calc 3 class, we want to talk about the double integral over the region of f of x comma y with respect to, the area. So d area really means this blue box down here. So instead of us having this interval here, so this really says that's the interval from a to b, our region now, since we're in 3 dimensions, the domain ends up being, your xy plane, or at least a piece of that. So this happens to be your region, so it's considered an area. So what we're going to learn eventually is that we can write this as a double integral from the integral from a to b, and the integral from c to d of your f of x comma y. C and d is going to be your dy, and then a and b is going to be your dx. So really, this is in terms of composition. So this double integral really means the integral with respect to x of the integral with respect to y. And there's going to be a theorem which is going to show us how we can change the order of these things. And if it's rectangular, actually, it's really, really easy. So we'll get to that in a minute here. But I really want to kind of build this idea from an example, and we're going to use your cross-sectional areas to kind of verify that this works out. So let me pause it, I'll draw a picture, and then we can see how this is working. Okay, so here's going to be our example. What I want to do is I want to find the volume under the surface, so we really want to do it in the first octave, where the surface being the blue function is going to be defined by f of x comma y is going to be equal to 4 minus x minus y. And we can see the region that I'm trying to find the volume basically, under. So the region is going to be this blue box, so we can see that, your x values are going to go from 0 to 2, and your y values are going to go from 0 to 1. Now, if you remember, like in a Calculus 2 class, we learned how to find volumes, and the way you would find the volume of something is this would be the integral over your interval. So let's just say from a to b of your cross-sectional area, and let's do this in say green, of your a of x dx. So this is where a of x ends up being the cross-sectional area. So what I'm going to do is I'm going to draw this a of x cross-sectional area inside of this. So we're going to slice this. We want to do it over the x's, so we want to run in terms of x's. So we're going to slice it this way. Now I'm trying to make this arbitrary, though it looks like it landed on x equals 1. Really, this a of x here, this cross section, is going to be sliding from x equals 0 all the way to x equals 2. So I can see that this is going to run from 0 to 2 of our a of x. So our job really is to figure out, how to find this cross-sectional area. So if we pull this off to the side, what we can see is I just only want that box there. I only want to investigate a of x. So if a of x ends up being this thing, and what we can see is the base of a of x is right here, which runs from 0 to 1, and then this height of a of x, ends up being part of this surface. So this is going to be 4 minus x minus y is going to be, that height. So I'll just call it f to simplify it. So what we can see is that this cross-sectional area here, this a of x, is nothing more than the integral from 0 to 1 of my function. So this 4 minus x minus y. Now remember this 0 to 1, what we're basically doing here, we're going back to the original, how do you integrate a something, how do you find the area underneath something. Notice that, this is now your y-axis and this is now your f-axis. So you're integrating it just through like a slice here. So as we slide here, we can tell that the y is ranged from 0 to 1, so that's why this is going to be dy. So that means, our a of x is this piece, so I can just plug this in here. So this is going to be the integral from 0 to 2 of, your a of x, which is going to be the integral from 0 to 1 of 4 minus x minus y dy, and then this is going to be dx. Now these parentheses are quite redundant, so I'm gonna get rid of them. So this is going to be equal to actually I'm going to slide this over here. This is going to be equal to the integral from 0 to 2 of the integral from 0 to 1 of 4 minus x minus y, and this is going to be dy, this is going to be dx. All right, so now just like when you do partial derivatives when we're going to take integrals, when I'm doing the inside piece, the integral with respect to y really means that everything that's, not y is going to be constant. So the integral of 4 with respect to y is going to be 4y. Integral from 0 to 2, this is going to be 4y. This is going to be minus xy because x is a constant. And this is going to be minus y squared over 2. And then I'm going to evaluate this from y equals 0 to y equals 1. Now when we try to first introduce these things, we tend to write x equals 0, x equals 2, y equals 0, y equals 1, just to kind of really reinforce that, these are your y interval and these are your x intervals. So when I evaluate it from 0 to 1, I know that this is in terms of y, so we still have our dx. So plugging in y equals 1, so this is going to be equal to 4 times 1 minus x times 1 minus 1 squared over 2. And then we're going to, I still have to have this integral from 0 to 2. And then we're going to plug in 0, so 4 times 0 minus x times 0 minus 0 squared over 2, and this is going to be dx. Now this entire piece is 0, so we'll just get rid of that. So now what we have is we have a function only in terms of x. So when I integrate this only in terms of x, that we're good. So this is going to be 4 minus a half, which is 3 halves. So, sorry, my bad, 3 and a half. So 3 times 2 plus 1 is going to be 7 halves. So this is going to be the integral from 0 to 2 of 7 halves minus x dx. So now we integrate. So this is going to be 7 halves x minus x squared over 2, and then we're going to evaluate this from 0 to 1. So plug it in 1 first, 7 times 1 minus 1 squared over 2. Then evaluate when you plug in 0, 7 halves, I missed the halves. So 7 halves times 0 minus 0 squared over 2. So this is going to be, make sure I got all this right. Oh, sorry, this is at 2. So these will be 2's. So 7 halves times 2 will cancel, so this will just be 7, and this is 4 over 2, which is 2. So 7 minus 2 is going to be equal to 5. All right. I was trying to slide this over because what I want to do is I want to show you that this really isn't the only way we can do this. What we can also do is we can slice this thing in terms of y instead. So let's kind of do that live. So I will try to erase this and not make a heck of a mess out of this. So if I want to slice this in terms of y, what I know is I can now go in this direction. Now what we can see is that this piece now is going to be the integral from 0 to 1, because this cross-sectional area right here is going to start at y equals 0 and slide to y equals 1. And now this is going to be, remember that this is 0 to 1, so this is defined in our y's. So this is going to be some a of y. So now reintroducing my cross-sectional area, we can really kind of see that it's going to look kind of similar. So this is going to be from 0 to 2. That's going to be your x values. So my a of y is going to be equal to the integral from 0 to 2 of 4 minus x minus y dx. So really kind of the goal here is to kind of prove that this volume, which is what we're actually finding here, this volume can also be written as the integral from 0 to 1 of my a of y, which is this, which is the integral from 0 to 2 of 4 minus x minus y. This is going to be dx because that's your a of y, and then you're going to have dy, which is right here. Now, if it's a rectangular area, it's really, really nice. You see that all I have to do is y goes from 0 to 1, x goes from 0 to 2, and that's still the same thing. X goes from 0 to 2, y goes from 0 to 1. So this is Fubini's theorem over rectangles. So I'll even write that out in a second here. So now we're going to integrate. So this is the integral from 0 to 1 of 4. We're integrating with respect to x. So this is 4x minus x squared over 2 minus xy. And then I have to evaluate this from 0 to 2. Remember, these are x values, dy. So then evaluating this here, we have our volume is going to be equal to the integral from 0 to 1, 4 times 2 minus 2 squared over 2 minus 2y, minus when I plug in 0, 4 times 0 minus 0 squared over 2 minus 0y dy. This piece again is 0, so I just have to integrate this. So this is going to be 8 minus, this is 4 over 2, which is 2, so this is going to be 6. So this would be equal to the integral from 0 to 1 of 6 minus 2y dy. All right, so integrating this is going to be equal to 6y minus y squared, evaluated from 0 to 1. So this will be equal to 6 times 1 minus 1 squared minus 6 times 0 minus 0 squared. So this is gone, so 6 minus 1 again is 5. So the volume of this thing is going to be 5 units cubed. All right, so let me write Fubini's theorem up there. I will do another example, and that'll finish this lesson. So let me pause it and clear this board. So this is Fubini's theorem. It says if f of x comma y is continuous throughout this rectangular region R, where R is defined from x being bounded between a and b, and y being bounded between c and d inclusive, then that means the double integral of our f of x comma y with respect to that area is equal to the integral from a to b of the integral from c to d of f of x comma y dy dx. And then we can see that we can change this to be equal to the integral from c to d of the integral from a to b of f of x comma y dx dy. Now notice that just to be sure that when we're integrating, we do it from inside out, so that these are going to be your y's, and then these are going to be your x's, so we're integrating this way. Similarly, we can see that x, of course, is bounded between a and b, and then y is bounded between c and d. So this works with a rectangular region that if you flip these, you're going to also flip the differentials. All right, so our example is going to be this. Evaluate. So I want the double integral over the region of root x over y squared dA. Okay, so I'm going to do this 2 different ways. I'm going to do it this way, and I'm also going to do it this way, so I'm going to have to define my region. So my region is going to be 0 less than or equal to x less than or equal to 4, and then 1 is less than or equal to y, which is less than or equal to 2. Now the beauty of Fubini's theorem says that it doesn't matter the way that you do it, you're going to get the same value every time. So there are times where one way will be easier than the other, and actually, moreover, there'll be times when one way will be integrable and the other one will not be integrable. So you'll have to choose one way over opposed to the other. So let's set this up. So in this case, first, what I'm going to do is, let's do it this way. So I'm going to do the integral from 0 to 4 of the integral from 1 to 2 of our root x over y squared. Now this 1 to 2 is going to be our dy, and this 0 to 4 is going to be your dx. Again, dy dx. All right, which means if I'm doing it with respect to y first, that means root x is a constant, so I can rewrite this as y to the minus 2, so the integral from 0 to 4 of the integral from 1 to 2 of root x y to the negative 2 dy dx. So this is going to be equal to, when I integrate with respect to y, this is going to be y to the minus 1 over minus 1. So this is going to be the integral from 0 to 4 of minus root x over y, root x over y be pretty, thank you, root x over y. And this is going to be evaluated from 1 to 2 dx. Okay, so now we're going to plug in, remember these are y values, so this is going to be the integral from 0 to 4 of minus root x over 2 minus a minus root x over 1. I'll just write the 1 there. So this is going to be dx. So now, now that you've integrated y and then evaluated it, we just are going to have a function of x left over. So now when you integrate this, this is equal to the integral from 0 to 4 of minus x to the 1/2 divided by 2 plus x to the 1/2. Actually, plus x to the 1/2. So x to the 1/2 and then minus half of x to the 1/2 is just going to be positive x to the 1/2. So this is going to simplify to this dx. Okay, so integrating this, we're going to add 1 to the power and divide it by it. So this is x to the 3/2, x to the 3/2, divided by 3/2, which is the same thing as multiplying by 2/3. So the 2's will cancel, and then we're going to evaluate this from 0 to 4. So this is going to be equal to 4 to the 3/2 over 3 minus 0 to the 3/2 over 3. That's going to be gone. Square root of 4 is 2, 2 cubed is 8, so this is going to be equal to 8/3. All right, so let's do it the other way. So we also know that this is going to be equal to this, you know, this volume is going to be equal to the integral from 1 to 2 of the integral from 0 to 4 of our, of our function. Now 0 to 4 is going to be your x's, and then 1 to 2's are going to be your y's. So now we're going to integrate with respect to x first, which means that y is constant, so this is going to be the integral from 1 to 2. A lot of people even pull out that 1 over y and then integrate this, this x to the 1/2, just to really verify that, y is a constant, so you can pull that out. It's not really necessary there. Same thing here. I could have put that root x over here. So this is going to be evaluated from 0 to 4. Dx and then dy. So integrating this is going to be y to the 3/2 divided by 3/2, so it's going to be 2/3 y to the 3/2. So this is going to be equal to the integral from 1 to 2 of 1 over y times that 2/3 x to the 3/2. And I'm going to evaluate this from 0 to 4 dy. Make sure that everything looks good. Did it slightly a different way. I don't want to mess it up. Okay, so so now plugging in 4, plugging in 0. So this is going to be the integral from 1 to 2 of 1 over y times 2/3 4 to the 3/2 minus. Now when I plug in 0, this is going to disappear, so I'm not going to write it. This is going to be dy. Now evaluating this, square root of 4 is 2. And 2 cubed is 8 times 2 is 16. So this is going to be equal to the integral from 1 to 2 of 16 over y dy. All right, so integrating this, this is going to be y to the -1, so this is integral from 1 to 2 of 16/3 y to the -1 dy. So this is going to be equal to 16/3 y to the -2 over -2 evaluated from 1 to 2. So this is going to be minus, this is going to be minus 8 over 3y squared evaluated from 1 to 2. Same thing. Pause this and just verify it before I make a mistake. Well, I found it. That was supposed to be a y squared, wasn't it? Boom. So y squared, so this would be y squared. This would be y squared. This will still be y squared. This will now be y squared. So this is going to be y to the minus 2. So this is going to be y to the minus 3 over minus 3. Okay, now let me verify. All right, so finally this is going to be, the integral of this thing is going to be 16 over 3 y to the minus 1 all over minus 1, evaluated from 1 to 2. So this is going to be equal to minus 16 over 3y evaluated from 1 to 2. So this is going to be equal to minus 16 over 6 plus 16 over 3. And there we go. We have 8/3 like before. Okay, so at the end, please consider liking and subscribing and for more content. Thank you.